The topic of inequalities is essentially an extension of equation solving. When solving equations, we are looking at particular values where both sides of an equation are of equal values. However, when solving for inequalities, we are looking for a range of values that satisfy the relationship between both sides of the inequality. In this video, we are going to look at how to solve simple inequalities involving polynomials. The main difference between an equation and an inequality is the sign that is used to establish the relationship between the left and the right-hand side expressions. In equations, the sign between both sides is always an equal sign, whereas for inequalities, the sign in between can be either greater than, less than, greater than or equals to, or less than or equals to. In an equation where the right-hand side is 0, we are essentially solving for particular values that cut the x-axis. So for example, if we have x squared minus 5x plus 6, we will be able to factorize it into x minus 3, x minus 2 equals to 0. And we know that this is going to give us the solution of x equals to 2 or x equals to 3. Graphically, how this looks like is, if we have an x-axis, our quadratic graph will look like this, and our quadratic graph is going to cut the x-axis at the points 2 and 3. And these are the two roots of the equation. However, when we are solving for inequalities, for example, if we are going to solve for x squared minus 5x plus 6 more than 0, what we can do is first factorize it. So x minus 3, x minus 2 more than 0, and we can now draw the same graph of having the roots 2 and 3 like this. And what we want now is the part that is more than 0. Now since I know that this is the x-axis, and if any y value is more than 0, it must be above the x-axis. Therefore, I'm looking for this part of the graph and this part of the graph, which tells me that all the x values that satisfy this inequality, it must be x less than 2 for this portion over here, or it must be x more than 3 for this portion over here. To solve higher order inequalities, we can apply the same graphing technique. The first step is to draw the x-axis and mark out all the roots. So we have the x-axis and the roots at 1, 2, 3, and 4. Next, we notice that since the highest power of x, if we were to expand this expression, which will give us x power 4, has a positive coefficient, that means that when x goes to infinity, x power 4 goes to infinity as well. So we can start from the top right hand corner, and we will then proceed to sketch the graph such that it cuts through all the 4 roots like this. Cuts, 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 and cuts again. Eventually, we will get a graph of this shape over here. Note that the exact shape of the graph is not important, as we just need to know which portions of the graph are above or under the x-axis. Now, since the inequality wants us to solve for parts of the graph that is above the x-axis, since it is more than 0, we are looking out for this region, and this region. And therefore, this tells us that the solution for this inequality will be x less than 1, or x between 2 to 3, or x greater than 4 for this portion, and this portion respectively. Take note that the method to draw the graph on the previous slide only works for roots that are not repeated or roots that have been repeated for an odd number of times. If we have repeated linear roots, we have to be careful to draw the graph correctly to reflect the number of times the roots has been repeated. As a general rule, if the root is repeated for an odd number of times, for example, 1 time or 3 times, then they will cut the x-axis. If we have an even power, for example, power 2 or power 4 or power 6, when the graph touches the x-axis, it is not going to cut the x-axis, but instead, it is going to simply touch and make a U-turn at these points. So touch and U-turn. If we are looking at this expression over here, we can draw out the x-axis and mark out the 4 roots 1, 2, 3, and 4, and start from the top right hand corner. Now we are going to touch the x-axis at 4 and 2 because of their powers, and it is going to be a cut at 1 and 3. So let's proceed to draw the graph out. Okay, starting from the top right hand corner, we are going to move downwards to 4, touch and U-turn, at 3, cut, at 2, touch and U-turn, and at 1, cut again. Since what we want is this expression being more than 0, that means we need to look out for this portion, and this portion, which tells us that the solution for this inequality will be x less than 1 or x between 3 and 4 or x more than 4. In this example, we have a quadratic expression x squared plus 4x plus 3, and we know that this expression can be factorized into x plus 3, x plus 1. So now we can transform this inequality into x plus 3, x plus 1 less than 0. Let's draw the x-axis out now and mark out the roots at -3, -1. And we can proceed to draw the graph from the top right hand corner, cuts at -1, cuts at -3. And the portion that we are interested in is the part that is less than 0, which means this portion over here, and therefore the solution to this inequality will be x between -3 to -1. In example 1b, we have a higher order inequality, but the approach is exactly the same. First, let's check if we can factorize this expression fully, and we know that we can change it into x minus 4, x plus 1 for the first quadratic expression, multiplied by x, and x minus 4 for the second quadratic expression. So now we have this expression being more than or equals to 0. And note that next we have x minus 4 appearing twice. That means I can simplify this expression into x multiplied by x plus 1 multiplied by x minus 4 square more than or equals to 0. Now note that this square over here tells us that it is a repeated root, and therefore since it's an even power, we have to do a U-turn when x is equals to 4. So if we draw our x-axis, the roots will be at -1, 0, and 4. And we are going to again start from the top right hand corner and move towards x equals to 4, and we are going to do a U-turn here, cut at 0, cut at -1. And the part that we are interested in is the part that is more than or equals to 0. So it is this part here, and this part here. And therefore, since the 0 point is also included, we will need to include this point and this point as well to get a final solution of x less than or equals to -1 or x is more than or equals to 0. In some cases, quadratic expressions can be factorized, and this makes it easy for us to find the roots and eventually solve the inequality. For example, we have this inequality over here which can be solved to give us x less than -2 or x more than -1 very easily. But what if the quadratic expression cannot be factorized? For example, we have these two expressions over here which cannot be factorized. How then can we find the range of values of x that satisfies this inequality? When we have a quadratic expression that cannot be factorized, the first thing to do is to check the discriminant of the quadratic expression, i.e. b squared minus 4ac. We recall from secondary school math that when b squared minus 4ac is less than 0, our quadratic expression will have no roots. What it means is that if I have this x-axis here, my graph either looks like this or like this, depending on the coefficient of the x squared term. However, if b squared minus 4ac is more than 0, we know that there will be two real roots, and two of the roots can be found using the quadratic expression over here. And therefore, we can say that the first root, if I name it as x1, it will be minus b plus square root b squared minus 4ac over 2a. And the second root will be x2 equals to minus b minus square root b squared minus 4ac over 2a. And with this, I will be able to factorize any quadratic expression into the form of x minus x1 times x minus x2, which is this form over here. Now, I have successfully factorized a quadratic expression which cannot be factorized that directly, but Since it is now factorized, we will be able to solve this inequality as per normal non-repeated linear roots. In example 2a, we have a quadratic expression inequality. First, let's check if we can factorize this expression. And we notice that we cannot factorize this expression, and therefore we will have to check the b squared minus 4ac of this term over here. So b squared minus 4ac equals to 4 squared minus 4 times 1 times 5, which gives us negative 4, which is less than 0. So we know that this quadratic expression does not have any real root, and therefore how it looks like graphically is, if we have the x-axis here, this graph will be entirely above the x-axis since the coefficient of x squared is positive. And therefore, since we want this quadratic expression to be more than 0, and we notice that the graph is always above the x-axis, the solution for this inequality will be such that x is all real numbers. Lastly, in example 2b, we also have a quadratic inequality where the quadratic expression cannot be factorized. And therefore, let's check our b squared minus 4ac. b squared minus 4ac will be equals to 3 squared minus 4 times 1 times 1, which is equals to 5, which is more than 0, and therefore there will be two real roots. So now let's solve for the roots of this equation using our quadratic formula. The roots will be equals to minus 3 plus minus square root of b squared minus 4ac, which is 5, over 2a, which is 2. And therefore, I can factorize this into x minus negative 3 plus square root 5 over 2 multiplied by x minus negative 3 minus square root 5 over 2 more than 0. And therefore, if we look at our x-axis, the two roots will be at minus 3 minus square root 5 over 2 and minus 3 plus square root 5 over 2, and our graph looks like this. For the part that is more than 0, we are looking at here and here, which tells us that the solution to this inequality will be x less than negative 3 minus square root 5 over 2, or x more than negative 3 plus square root 5 over 2.